This is for my people who just lost somebody. Your best friend, your baby, your man or your lady. Put your hand way up high. We won't ever say bye. No, no, no. Mama's, daddy's, sisters, brothers, friends, and cousins. This is for my people who lost their grandmothers. Looking at us now. We won't ever say bye. As a child, there were no times I didn't get it, but you kept me alive. I didn't know why you chose. Sometimes it's sudden mornings and I miss you. The love you taught me, I'll be home for days. Deprivation brings. You never let me know, you never let me show because you love me. You never give me so much more to say. You were with me for anything to do. Never knew I could have like this. And everything I love was in me. Wish we could together, but I wish we could come back to cry. I'm saying you is my everything. But every moment I see nobody needs to do. Talk about you soon. No honest thing to do.
Okay, here's an example of a differential equation with a nice solution to it. And this comes from a friend of mine, Spencer Gray, who's a pilot. He flies 767s among other planes. But he asked me once, if the plane is on the ground and you're flying on the ground and you're driving up to the gate or on the taxiway or something, and you turn the plane such that the nose wheel lines up with this line that you're supposed to be following. So say the nose wheel is right about here, and you turn the plane so it's going to line up with a straight line. And so as the plane moves forward, you keep the nose wheel aligned so it moves this way. And as the plane moves forward, then the back end slowly ends up swinging around until it's eventually lined up or pretty close to lined up along that line. And so the question is, if you have the plane in some initial position like you see here, and you turn the nose wheel and maintain course so the nose wheel tracks along that line, how long does it take the back end of the plane to swing around so it's also lined up with that line? And the answer is that it never completely lines up. It gets really close, and we can see how long it takes to come within a certain distance, but it never actually gets there. And we'll set up the equation and solve this and see why. So the trick to these problems is always in setting them up correctly. So let's look at the diagram here. This is the front wheel of the aircraft, and the back wheels are probably about right here. And so we're going to be looking at this distance, this line segment right here, and we'll call that length L. Okay, those 2 points are the points that basically determine the rotation of the plane. And as the plane moves forward, it's moving right now in this direction. And the distance that it moves is we'll call that x, is going to be the velocity times the time. So we need to think here in terms of differential quantities. If it's moving just a tiny little bit in an infinitely small amount of time, then the distance it moves is an infinitely small distance dx during this infinitely small time dt. So dx is equal to v dt. Now as it moves, this distance here we need to concern ourselves with. That's the distance y. And we're basically asking, how long does it take for y to get to 0 or to get really close to 0? Because once y gets to 0, the plane is basically lined up with this line. So we need to figure out what to do with y, and see the little red arrow there that indicates the motion of the plane. As the plane moves forward a distance dx, if that were dx right there, then there would be this little corresponding vertical component of that, which would be dy. So dy is the little incremental change of the distance of the back wheels from the line. And we need to name this angle right here. We'll call that theta, that angle right there. And you can see that the distance or the rate at which the back wheels approach the line is not the velocity of the plane. It's the velocity times the sine of theta. So we can write this little equation. dy is going to be v dt times the sine of the angle, and we also need to introduce a negative sign right there because dy is getting smaller as the plane moves forward, as the velocity of the plane moves forward and time is going forward, y is getting smaller, so that negative sign takes that into account. Now, we could solve this equation, but we have two variables here. We have a y here and a theta here, so we need to get theta in terms of y. And fortunately, that's pretty easy to do. If you look at this little right triangle here, you can see angle theta has y as the opposite side and L is the hypotenuse. So it's pretty easy to see that sine theta is y over L. So we can just substitute that right there for sine theta. And so we can write dy is equal to negative y over L times v dt. And you see the v dt was right there, and the sine theta was written right there as y over L. And we still have the negative sign. And now we'll just rearrange this a little bit. I'm going to write dy over y is equal to negative v over L times dt. And then we can solve this by integrating, so we integrate both sides. And the integral of dy over y, I'm going to come up here because I'm running out of room. The integral of dy over y is the natural log of y, and we have our negative v over L, and the integral of dt is just t, and of course we have to add a constant of integration. Now to solve this for y, we need to exponentiate both sides with base e. A base e exponent will get rid of our base e logarithm, so y ends up equaling negative v over L t. Excuse me, that's e to the power of negative v over L t, and I'll write it like this, negative vt over L plus c, and all of this is up here in the exponent position. So let's deal with that for a second. This is going to be, I'm going to call this constant, I'm going to call it C1. It doesn't really matter, it's just a constant. According to the laws of exponents here, if I have these two exponents added together, that's equivalent to this, e to the negative vt over L times e to the C1. And if C1 is a constant, then e to the power of C1 is a constant. So I can say y is equal to e to the power of C1. I'm just going to rename that as some other constant. I'll call that c. So c e to the negative vt over L. And we can figure out what this constant is. Exactly. And it turns out to be pretty easy and intuitive. We just say that at time 0, so when we have a 0 here for this t, at time 0, the equation will look like this. Y will equal to c times e to the 0. And e to the 0 is just 1 because e to the, or anything to the 0 is 1. So at time 0, y is equal to c. So that means c is the initial y position. So c has to be c is equal to the initial y value. So here's our equation, and I'll write it in the middle here just because that's the only place I have room. Y is equal to y0 times e to the negative vt over L. So now let's take this equation and work out an example.